In this video, we're going to break down inclined planes, right? So problems involving inclined planes with its forces, but primarily we're going to be looking at forces, but we're also going to mix in a lot of kinematics in there as well, just equations of motions and so on, right? So the presumption here is you're kind of familiar with flat surfaces, right? Because we've looked at those in previous videos, right? So if you're familiar with flat surfaces, we are going to keep a similar approach, but we're going to tweak a couple of things just to make our lives easier for inclined planes, right? So just to remind ourselves, right? So the first thing that we need to remember are the four common forces, right? Acting on an object that is on a surface, that's moving on a surface. When it came to flat surfaces, right, we're just going to remind ourselves that, okay, because a dot, this basically represents the center of gravity of an object. So all the forces are acting on this point. So the four forces were weight, which is always going to be downwards. We have an applied force, which was, which can be in any direction. So this is weight. This is F applied. We have friction. If the, object, friction is always going to oppose motion, right? So if your object is moving to the right, friction is going to be to the left. And if your motion is to the left, friction is going to be to the right. And then you also have a normal force. Normal force, this comes from Newton's third law. Essentially, this is the reaction force from the surface that you're on. So if you are on a flat surface, that is going to be, and basically because you're on the surface is basically also pushing you up. So this is your fourth and final force, right? So these were our four forces when it came to flat surfaces. And essentially the approach was, because you have two separate planes, two separate axes, your y and your x, we had to resolve all our forces into y's and x's. Anything that wasn't explicitly in either y or x, we had to find the components of these forces. So in this case, this would be force applied. So you had to find the vertical component of that force and the horizontal component of that force using trigonometry. Right, terrible sketch, but essentially that was our approach, right? So we're going to take a similar approach with inclined planes. Again, we're going to represent the center of gravity with a point, right? And these are going to be our forces. What I'm going to do is we're going to draw a slope, right, just to give us guidance of where we are. Right, terrible drawing, but okay, we're going to call this theta, right? So hopefully you can kind of see. I know the color's terrible, but I want to put darker colors for the forces, right? So this is our point, right? Now, again, we're going to ask ourselves, what are the different forces that are going to act, right? So we have four common forces. In what direction are they moving? The first one is going to be weight. Weight is always going to be directly downwards. So this one doesn't really give us problems, or at least not yet, right? You have applied force. In this case, we're going to assume that this is being pushed up or down the slope. So let's assume that this is being pushed up the slope in this case. So this becomes force applied, right? We also have normal force. Now, again, because this comes from Newton's third law, right? Your normal force, yes, in this case, it's always going to be directly upwards. But the thing that we talked about when we talked about different kinds of forces was that normal forces are always going to be perpendicular to your surface, because it is basically your surface pushing you back, right? So if your surface looks like this, your normal force is going to look like that. If your surface looks like this, your normal force is going to be perpendicular and it's going to look like this. So in this case, our normal force is going to be something like that. And that is our N. And then if your friction is always going to oppose your motion. So if you're moving up the slope, your friction is going to move in that direction over there. So that's force of friction. All right, let's just remove these. Okay, right, so these are the four forces that we're usually going to be using. Now, the problem is, if we were to use the same approach and say, okay, because we're going to need to find resultants of these forces, right? We need to find the x and y components of these forces. If our x and y were like this, that means that your normal force would need to be resolved. Your frictional force would need to be resolved. Your applied force would need to be resolved. That would make our life really, really difficult. So what we're going to do is we're going to slant our axes. So instead of having axes that look like this, our axes are going to look like this, where your x-axis follows the slope, right? The direction of the slope, and your y-axis is perpendicular to that slope. So let's just come back here. So we already have our x-axis, which is in that direction. So we're going to draw this as x. And then our y-axis is basically going to be perpendicular. So it follows the normal force. So this is going to be our, just remove this, y-axis. Hopefully that, it's visible. But yeah, the moment we do this, this is very convenient for us because normal force is on the y-axis. We don't need to resolve that. Force applied, yes, we can, make, your examiner might make your life difficult and make it like this. But for now, it is basically along the slope. So that's fine. So we don't need to resolve that. Your frictional force is going to be always along or perpendicular. Parallel to the road, parallel to the slope, parallel to your direction. So we don't need to resolve that. The only one we would have problems with would be weight. Right? So now we need to use trigonometry to resolve weight into its vertical component. We need to ask ourselves how much of it is going in this direction, how much of it is going in that direction. All right, so let's just bring this back. So in order for us to do that, right, we need, let's just draw that as a triangle, right? So it has the weight is going down in this way. But we also need to know how much of it is going in the y direction, which is in that direction. How much of it is going in the x direction, which would be, yes, it is in that direction for now, but for now, let's just draw it like that so that we have a right angle triangle. How do we know that this is a right angle triangle? Because we know that this is the y-axis, this follows the x-axis. Y and x are always at 90 degrees to one another. So this is the this is W, this is your weight. This is your weight in the x direction. This is your weight in the y direction. Right, that's perfectly fine, right? But in order for us to get the weight in the x and the weight in the y, we need to know an angle. So we're going to try to look for this angle here, right? But actually, you've already been given that angle. It's actually this angle theta over here, right? Which is a little bit hard to see on face value, but let's just explain that for a little bit. So we're going to remove all of this stuff here. And we're going to try to explain why this angle is the same as that angle over there, right? So in order for us to do that, we're going to draw two lines. We have this line over here, which is basically following up the slope. And we also have, let's go for a different color. We have this line over here, which is the ground. So we know that this is going to be theta, right? Essentially, if you take, all right, so what we're going to do is we're going to take these two. Okay, let's do this. Oof. Okay, that did not work out. Okay, so let me do this instead. All right, we're just going to draw it as one line, like that. All right, so this is our theta. All right, so we know that that's our theta, right? So what we're going to do is we're going to take this same line over here. Let's just copy that. Right, maybe let's change its color. We're going to make it red. Right, so we're going to take this, and essentially, so we know that this angle over here within the line is theta, right? Now we're going to rotate that. So you can see that this line over here is the one that's horizontal. What if we made it vertical? Because the weight is vertical. So we want to see, okay, if I put this line so that it's the same direction as the weight, which basically is in that direction. It's not too accurate, but right, so that would be your weight. So this direction would be our weight, but as you can see over here, because we've turned this line as well 90 degrees, this was our x-axis. Now once you turn it into 90 degrees, this is now your y-axis. So we've kept that same angle, which was theta, right? And this was now our weight, this was now our y. So the angle between the weight and the y is the same as the angle between the horizontal and the x-axis, because you've basically turned the whole thing 90 degrees. So since this line over here is perpendicular to that line over there, and at the same time, let's just group them, this line over here is perpendicular to that line over there, the angle between the two pairs is the same, All right. So once you have it like this, so once we've understood that, okay, this theta is equal to that theta, right? So maybe it doesn't make too much sense, but as long as you remember that this theta, whatever theta you get over here, is the same theta as the weight, the angle between the weight and the y-axis. So once you have that, that means for our Pythagoras, we now have an angle and we have the weight. Okay. Now, weight in this case is our hypotenuse because we've broken it down. Because remember, hypotenuse is basically the one that is opposite the 90 degrees. I know this is it's a little bit weird to see because the triangle is slanted. But if you look at a right angle triangle, the 90 degrees is here. If your angle theta is there, your hypotenuse is always going to be opposite to that. Your other two angles are the ones that are 90 degrees to one another. So, I mean, your other two lines. So that's going to be your WY and your WX. All right. So once we have that, right, so now we can say, okay, we have the hypotenuse. Let's start with WY, right? So the weight along the Y direction. In this case, this vector here is between theta and 90 degrees. That makes it the adjacent. So we have cos in this case. So cos theta is equal to adjacent, which is WY, over the hypotenuse, which is W. So WY, if you make it the subject of the formula, that's going to be W cos theta. Same thing here. This is going to be this line here. Let's just remove that. This line here is opposite the angle, which means WX is the opposite. Since it's the opposite, that means we need to use sine. Sine WX over W. Same thing here. This is basically going to be W sine theta. So essentially, we do all this to say this, right? You have these three forces: force of friction, normal force, applied force. But the W, the weight, has to be resolved so that it's also slanted, since it's always going to be vertical. Once you've resolved it, right, so you're going to have a system of forces that looks like this. I'm just going to remove this. All right, hopefully this made sense, right? But now our forces are as follows. Let's just redraw the slope again. Oh my goodness. Okay, that works. All right. If this is our theta, right? So this is our theta. Okay. We have four forces, right? So let's start with the ones that we didn't have to resolve. Applied force goes in that direction. Again, I'll emphasize that this might change. Maybe the question might be a bit more complex, right? So you've got applied force. You have the normal force. That's going to be perpendicular to your surface. You have the frictional force, which is going to oppose, right? So you just have to be careful if it's, frictional force. If this is normal. If your motion is down, that means frictional force is going to oppose your motion. Wherever your motion is, your friction is going to oppose it, right? Now, weight, just be careful about the angle. But for now, if this is our theta over here, if this is our theta, that means we have two components of weight. We have the y component of weight, which is in this direction. And that y component of weight is your weight cos of your theta. And then over here, yes, we have the force of friction, but we also have another weight component that's going down here, right? So that's the same as this one over here. It's going down the slope. So that component of weight is going to be down the slope, and it is W sine theta. So now in total, we had four forces, but now we have five because we have the first original three, but we have a fourth one that was resolved into its y and x components. So essentially, this is the approach that we're going to be taking, right? So this is the one change. I know it looks a little bit more confusing, a lot more confusing because everything is at an angle. But once you kind of get, why, especially understand this triangle over here and why this angle was like that, and then also the WX. Also be careful of the angle that you're given. Sometimes they might want to throw a trick in there, but we'll do as many questions as possible, obviously. But for now, essentially, this is how we're going to approach this. All right, so we're going to stop this video over here, right? So we'll call this part 1. From part 2, just that the video isn't too long, we're going to continue from this point. All right, so hopefully this was helpful, and I'll see you in the next video.